Welcome back to Decaf-Math, and welcome if you are new here. So let's go over a property of functions, specifically whether a function is even, odd, or neither. And yes, we're talking about functions being even or odd, not just numbers. So we'll look at this both algebraically, so working directly with the equation, and graphically, so based on our picture and our plot. And we are jumping around a little bit with topics, so as usual, feel free to browse the playlists on my channel page, and we will keep building our way and working our way through a whole bunch of topics. And I will try to link relevant videos the best I can, and I'll just try and order them in a somewhat logical way. Okay, so for even and odd functions, let's just start with the, too long, didn't read, the TLDR. Just the takeaway here. For even functions, f of negative x equals f of x for all x. Okay? And we'll get into what this means. So that's the algebra way, just writing it out with an equation. And graphically, it means that the graph of f is symmetric about or across the y-axis. The y-axis. And then we'll just go over the odd part just so that we have it all in one place. And then at that point, you can drift off if you haven't already. So, for odd functions, f of negative x equals negative f of x for all x. Okay? And for this one, the graph of f is symmetric about the origin. Okay, and that is it. That is all that we're really going into today. But of course, the rest of the video is going to be, what on earth does this mean? But if you just want to memorize this and kind of wake up and surprise yourself for knowing random new math, go ahead and memorize these two equations. F of negative x equals f of x, and f of negative x equals negative f of x. Okay, so let's take a look at this a little bit more. So what this means is for even functions, basically, actually, I guess first of all, I will try to link in the info box our intro to functions video, because that is going to be really important for our notation here and to really understand the concept of input and output. So with this notation here, it means that I am plugging in an x. X is sort of like my placeholder. And my function is sort of the set of instructions. At least that's how I like to think of it. It's kind of like the set of instructions for what to do with your input to give you a corresponding output. Okay. And functions by definition have to have a clear output for each input. So it needs to be defined. And it needs to be like, you need to have one output. So I can't input 2 and then my function give me 5 sometimes and -1 sometimes. It needs to have a clear output. So with this notation, let's just start with like an example, and I guess we can work through a few today if we have time. And then we can do more practice together. But let's say I have a function, just to build some intuition about what this notation means. Let's say we have f of x equals x squared plus 3. So here we go, we have our function and it is defined. Okay, and if you've studied it already, then you'll know that this looks like a parabola. But the f of x part, for instance, let's say we gave an input of 3. So f of 3 is this just means I'm plugging in 3 for x. It's with my input of 3, what is f of 3? Well, this function by definition tells me I take an input x, which is just a placeholder, and the output that I'm going to get is that number squared, meaning that number times itself, plus 3. And so f of 3 is going to be 3 squared plus 3. And 3 squared is 3 times 3, which is 9, plus 3, which is 12. So f of 3 is 12. So if I input 3, I get an output of 12. So what this tells me is if this function is even, then I would expect that if f of 3 is 12, I would expect that f of -3 is the same thing as f of 3, which is 12. So I would also expect f of -3 to be 12. So we can kind of try this. So f of -3, meaning I'm inputting -3. So that means -3 squared plus 3. And the negative number squared, so -3 times -3 is positive 9. Plus 3 is also 12, and those two are equal. So this isn't sufficient. I'm just picking a 3. That's not this 3, and that's just a random input. So it's not sufficient that just because f of 3 equals f of -3, that this function f of x equals x squared plus 3 is even. That is only one particular x, so this has to apply for all x. Okay, and so it's not sufficient to just say this, but I wanted to do this specific case to kind of really show you what this x and -x is doing here, what's going on, right? So that's just to build a little bit of intuition. And so for the odd case, if I have f of -2, for instance, if I had a function and I plugged in -2, if it equals that value, whatever that is, I'm plugging in -2 in place of all the x's, then if it happens to equal negative of f of 2, positive 2, so negative f of 2, then, and that's true for all x's, then that function is odd. So it's just about working with f of -x. In both of these cases, you can see the part of the definition is the f of negative x, and seeing if that happens to equal f of x, which is the original function, or negative of the original function, the function that's given. Okay, so that's pretty much all we're doing. Okay, so let's try, so let's write the actual step and let's try this particular example. The f of x equals x squared plus 3, but let's see if it's even, odd, or neither. And I kind of just gave away that it might be even, but like we said, it's not sufficient to just pick a random number. Okay, I just did that for the sake of, like I said, just to remind you what this negative x and this x is doing here. So, I mean, it's pretty much a similar process, but to show for all x, so if you don't know if the function is even or odd or neither, and it might be neither, up front, then you can just start by finding f of negative x, because for both the definition for even and odd, you have this f of negative x going on the left side. So we start with that. So let's figure out what f of negative x is. And to find what f of negative x is, like we kind of figured out intuitively here, but what this means is we're putting in negative x as my input. So this notation often gets confusing, and so you're not alone if this kind of trips you up, but I might be like super honing this in if you already know it, but it doesn't hurt to really make sure we know what we're doing. So f of negative x means I am going to plug in negative x in place of all the x's in the function. Okay? And when you do that, put parentheses everywhere that's necessary. Meaning, if this says, okay, so this tells me I take my input and then I square it and I add 3. So it just so happens that my input is going to be negative x. So I'm going to take that input, negative x, I'm going to square it, and then I'm going to add 3. And so I put parentheses here because the instructions say square that. So square the whole thing. So when in doubt, just put in your parentheses. Okay? So I think what gets tricky here sometimes, and just ignore this if you never get confused by this, but is that this x is not this x. Like, people might be like, oh, negative x, so I'll just put a negative x squared like that. But this x is like a placeholder, okay? Like, this is just f of any input, f of stuff equals that thing squared plus 3. So f of heart equals heart squared plus 3. Okay, so this x and this x aren't really, they're not the same x. It just so happens that my negative x is my input. Okay, so you might as well say f of cow equals cow squared plus 3. But cow just happens to be negative x. Okay, so literally plug in negative x in place of all the x's in my function. Okay, so from there we are going to simplify. So simplify negative x squared is x squared, and this is why parentheses are important, because it's not negative x squared, it's negative x squared. So that's positive x squared, and you probably already know that by now with your squares, but negative 1 squared is positive 1, and then x squared is x squared, so 1 times x squared is x squared. So You can use your exponent rules, or you can recognize that a negative times a negative is positive. So you have x squared plus 3. And so you simplify. So I guess step 1 is plug in negative x in place of all the x's in the function. And then you simplify, and then I see that x squared plus 3 happens to equal my original function. So once I simplified this algebraically, I got x squared plus 3, which equals my f of x. So I basically just generalized the f of 3 case for all x, plug in negative x, simplified, and realized that I got the original function. So this function is even. Ta-da! Okay. So, not to be totally predictable, but let's try another example. Let us try f of x equals x cubed minus 2x. Okay, so this is my function. And so I don't know whether this is even or odd up front. We're just going to try. So the first step is plug in negative x in place of all the x's. So we start with f of negative x. And so I'm putting in negative x in place of all the x's. And remember to put parentheses. So we have negative x cubed minus 2 times negative x. Okay. So again, we're just putting in negative x as a unit. So put the parentheses around that unit if it makes the calculation here confusing. But f of x equals x cubed minus 2x means I take my input, I cube it, and then I minus 2 times that input. And of course, order of operations, so multiplication happens first before the minus. So now we can simplify this algebraically. So negative x to an odd number 3 is still negative, so negative x cubed, and then negative 2 times negative x is plus 2x. And I've pretty much simplified it, right? So that's as far as I can go. And so straight away I'll notice that this is not equal to my original function. Negative x cubed plus 2x is not x cubed minus 2x, right? These two are not the same, though they look pretty close. And so the other thing I will try is, so f of negative x is not equal to my original function f of x, but I'll try negative f of x. So if I pull out a negative from this, a negative 1, I factor it out. I have an x cubed minus 2x, right? Or alternatively, you can start with your original f of x and say negative f of x is negative of x cubed minus 2x, and then distribute this negative to get negative x cubed, and then negative times negative is plus 2x. So you get that, or you can factor. So either you distribute it in or you factor it out. So this, once I factor out this negative, I get negative, and then this stuff on the inside here is x cubed minus 2x is my original function, negative f of x. So I have f of negative x equals negative f of x. Negative f of x. I hope you can see that. So that is odd. So this function is odd. Okay. And so once you try this f of negative x thing, and if you can't get it to equal f of x, and it's not equal to negative f of x, then of course it is neither. But that's it. So step 1, plug in negative x in place of all the x's. Step 2, simplify algebraically as best you can. And then step 3, notice if that simplified expression is equal to your original function or your given function, or if it happens to be equal to negative of your original function. And so then, depending on which, if either, then it's even or odd, and otherwise it is neither. Okay, that's it. So graphically, this has some implications, and this is pretty much why we study them. Oh, and before we do that, I should mention that you might notice here, like, this exponent is even, so you might just think that the whole thing is even. And intuitively, that's like a really cool and good intuition to build. I mean, the exponent is kind of even, and intuitively you can think of it as, okay, negative x. If I put in a negative x here, that's going to become a positive, so it looks like it would be sort of symmetric there. The safest thing is to just work the whole thing out, okay? Just because, you know, the rest of this part, it might look like it should be even, but like the rest of this part might throw you off a little bit. So just make sure you're actually checking the whole function, okay? And sometimes it's not even just a polynomial like this. You might work with like trigonometric functions and stuff like that, and you know, like you might have something in the denominator like rational functions. So we don't really want to generalize, but you'll start to see some patterns as you work through this, okay? Okay, so anyways, graphically, just straight from these definitions here, we can kind of see what it'll look like in a picture. So the first thing is, if f of negative x equals f of x for all x, the reason this is symmetric across the y-axis. So what does that mean? It means that this is my y-axis. So I just kind of drew these just because I didn't want to, just wanted to save some time in this video, but I drew the x and the y-axis. You can label what the scale is on your own. But basically, if on a graph, and we haven't quite talked about this here on this channel yet, we've talked about plotting points, and points are x comma y. So we kind of talked about it, but not with this notation. But f of x is my y. So I'm going to group together my x comma y, where y is based on my function, my output when I input x. So f of x is my y, and when I group them in this way, I can get plots of my graphs. But anyways, we'll get there, and we'll make our way toward this if this part's kind of confusing for you right now. But if you're learning about even and odd functions, and you're learning about graphing them, this basically is saying that the y coordinate that is associated with x is also equal to the y coordinate that's associated with the negative x. So like when we just tried the special case of f of 3, when f of 3 was 12, I think it was, for our other example, and it's f of negative 3 is also 12. That means that when we plot those points on my curve, I would have 3 comma, you know, based on your units, but 12 and negative 3 comma 12. So whatever it is here, that's not 12, but you can scale it. But 3, 1, 2, 3 to the right goes up 12. 1, 2, 3 to the left also goes up 12. It's just as long as it's symmetric. See? Because for any x that I go this way, I'm going to have f of x as my y coordinate for that point. And then if it's an even function, my f of negative x is going to equal that. And f of negative x means my x, meaning my x coordinate left, negative x, I mean, assuming x is positive, right? You can think of it the other way, but it's the same because negative of -3 is +3. So whichever way you want to think of it. But if I go 3 this way, I have a y-coordinate of f of 3, whatever that is. If I go 3 negative, it's also equal. Then basically anything that I go here, I would go the same vertical y. And that gives me a plot, whatever that looks like in the end. It's going to give me something that's symmetric. Let's just, let's just put a parabola. Why not? This is probably not even actually parabolic. I'd have to calculate the equation of this based on 3. But you know what I mean? Like, it has to end up being symmetric about this y-axis here because of the equation. So if x goes a positive this way and it has a corresponding y value of f of x, then, and that equals to the y value corresponding to f of that negative x, then whatever's on here has to be equal here, whatever's here has to equal here, and that's what it means to be symmetric about the y. It folds across. Okay, so if you have a function that is symmetric about the y, you know that it is even. And so for odd, this is a little bit weirder to visualize, but it's not too bad. The graph of f is symmetric about the origin. Of course, this has nothing to do with the orientation, right? Like this could go, it can have weird stuff going on in between as long as it, I'm not drawing this super accurately, but as long as it is symmetric. Oh man, whatever that lines up to, but you get the idea, right? Like it can fold, but it doesn't matter what the actual shape is as long as it's actually symmetric. But here, for it being symmetric about the origin, for odd functions, f of negative x equals negative f of x. So that means that if I have, 3, let's pick the 3 one as an example. My f of -3, whatever that is the y coordinate associated with the x coordinate of -3. So when we start plotting these points, it's going to have, -3 comma f of -3. So my y coordinate is what this tells me. So for x is -3. Okay, so it's hard to say out loud because it's depending on if I'm saying x itself is -3 or if I'm saying the whole input is -3. But let's start with this side. So if x is 3, okay, if x is 3, this is telling me that f of -3, so the y coordinate at x is -3 is equal to negative of the y coordinate when I plug in x is 3. So if I have f of -3 is, or let's say f of 3 is 5. Okay, this is my point here. 3 is 3, 4, 5. Okay, let's say that is f of 3. So this is the point 3 comma f of 3, where f of 3 is 5. Okay, then if that y coordinate, the f of 3 is the y coordinate, so that's 5. -5 is the y coordinate associated with f of -3. So -3 comma -1, 2, 3, 4, 5. So -5. So this would be -3, -5. So if I'm given an odd function and I know f of -x equals negative f of x, and you take this for every single point, so if I had some value of f of 1, let's say f of 1 is 1 or whatever, 1, or I'll just kind of, let's make it smooth. So let's just pick like this point. I don't know, like that point. So let's say 1.5 comma 1. Okay. If 1.5 is my x, so that's a positive x, and my y is 1, then f of negative 1.5 is negative 1. So f of negative 1.5 is negative 1. Does that make sense? So just pick specific values here and know that when we graph, our input is the x part and the output is f of whatever, so f of that x. Okay, and like I said, it's really hard to say out loud because the f of the negative x is like, am I talking about positive x's or negative x's? And am I talking about the input x or am I talking about like the absolute value? But I hope this is making sense. So if I have a shape like this, which is something like that, okay, that is symmetric about the origin. That's what it means to be symmetric about the origin. It's kind of like rotated. It's rotated, so it should be symmetric. It's rotated and it flips across itself. So it's almost like flip across this and then flip across that, and that is a rotation about the origin. Okay, so let me know if this part is still confusing, and we can definitely graph some more examples to take a look, but I hope that kind of helps build some of the intuition. So for even functions, they're symmetric about the y, and for odd functions, they're symmetric about the origin. And it could look this way too. Okay, like it could go this way, as long as for each point here with the corresponding like x here, you get the negative, and this isn't a perfect drawing, but you get the negative y, like that. So here in opposite x's, you get opposite y's, that kind of idea. Okay, so here's a little food for thought and a question for you. Why, for even or odd, why do I not have a situation where it says the graph of f is symmetric about the x-axis? So why would I not have a situation where I say some function like this? I'm just sketching this, but you can actually be more precise, but like that. If you want to think on that one, you can pause this for a second and think about it. But the reason is because for functions, you're not going to get a function that has a graph like this because it doesn't pass the vertical line test, which we'll go into. But if you've studied this already, then you know that for functions, you would expect, since each x has a clear output, a clear y output, it needs to pass the vertical line test, meaning there should only ever be one point that intersects a vertical line. And if there are multiple, 2 or more, it means that it's not a function, because at, say, this x of 2, you have 2 y values, and that's a problem. So your graph of a function should not ever look like this anyway, so you don't need to ever have a graph that is symmetric about the x-axis, the graph of a function, at least, right? So we're really talking about symmetric about the y and symmetric about the origin. So that will come in handy when we are graphing functions or just sketching functions. And I know I'm kind of scribbly right now, intentionally so, but we will graph this a lot more precisely when we have specific functions that we're working on and that we are analyzing, and we will do a lot more work with that both in algebra and precalculus and calculus. So I hope that this was helpful. The main takeaway is still just this part Usually in solving these equations, figuring out if it's even or odd, it's easiest to just use the original equations if you're given them. And if you're given just graphs, if you have like A, B, C, D, which of the following are even, odd, or neither, or whatever, you just need to look at the symmetry. Okay, let me know if you have any other questions. We will pop on, maybe do a whispered video with more practice. The rest of it for practicing these types and trying out if it's even or odd or neither, it's really about being careful and remembering your algebra and your algebra rules. So this might be some fun review or practice, or I'll try and point out common mistakes when people try and simplify stuff, but with enough practice this will become second nature if it isn't already. Okay, I will see you around very, very soon. Thank you so much for hanging out with me. As usual, let me know if there's anything else that I can support you with, and I send you all my love. Bye bye.